Hi guys, today we're going to talk about the Lagrange multipliers and slack variables and how we can use those two things in conjunction to solve the Rosenbrock function subject to certain constraints that we're going to be going through. Today's specific constraint is going to be x naught squared plus x1 is greater than or equal to 1, and we'll just be using those two things, slack variables and Lagrange multipliers. And don't worry, I'll explain those two, and we'll go through that, and we'll solve the Rosenbrock function subject to our constraint. So stay tuned. Hey guys, so I wanted to start out the video talking about Lagrange multipliers and slack variables and kind of explaining what both of those are. So we're going to start out with Lagrange multipliers. And so Lagrange multipliers is purely a geometric idea, and it basically states that the gradient of a function is always perpendicular to that of the function itself. So as you can see over here, we have the function itself, and then we have its gradient, right? This red line is the gradient, and these dotted blue lines are our functions of x and y. And essentially, we can use this idea that the gradient is always perpendicular to the function to interpolate that and kind of think that it gives us the idea that we can, at the minimum, our gradient and our function will be collinear. So you can see right here in this sketched diagram, we have the minimum of our function, and we have the gradient, right, which is perpendicular to our function at all times. And at the minimum, they are collinear, which means they're both going the same direction. So that's basically what the idea behind a Lagrange multiplier is, and it's a purely geometric idea. Next, I'm going to talk a little bit about slack variables. So the thing with slack variables is it's basically a way to convert an inequality to a regular equation. In this example right here, we have y is greater than or equal to 0, and then the inequality ax is greater than or is less than or equal to b. And we can convert that equation, or convert that to an equation, by combining two things together. So basically, we can add another random slack variable to create a regular equation given an inequality. And we're going to be using that in our Python code later. So that basically explains the Lagrange multipliers and their slack variables, and we're going to use them in conjunction to solve the minimization of the Rosenbrock function subject to the constraint that we talked about before. Okay, so let's start coding our Rosenbrock function. So I wanted to talk about what the Rosenbrock function is first, and it's just this guy right here. So it says function of x of y is equal to a, which is 1, minus x squared plus 100, which is our b value, times y minus x squared squared. So we're going to write that out in our code. So define Rosen of x, and we're going to have it return just the Rosenbrock function, which over here is 1 minus x0, our first x, or just regular x, right? And then y is going to be our x1. And that would be squared, plus 100 times x1 minus x0 squared, and we're going to square this value as well. And now we should have our Rosenbrock function defined. The next thing we're going to want to do here is define our constraints. So as we talked about before, we're going to be using the constraints right here. X naught squared plus x1 is equal to or less than 1. And we can use a slack variable here and just create a slack variable so that we can turn that into an equality. So we're going to do define constraint of x, and we're going to have it return our constraint, which right here is what we have. But if we want to turn this into an equality, we can just add another slack variable, so some random value, right? And set that equal to 1. So what we're going to do here is we're going to do x naught squared plus x1 plus x2 squared, and we're just creating x2 as our slack variable, and that would be equal to 1. So then we're going to do minus 1 here as our minus 1. There we go. We're going to do minus 1 as our constraint for this particular problem. So the next thing we're going to want to do here is, remember with our Lagrange multipliers, our gradient is always perpendicular to our function. So what we're going to want to do here is we're going to want to define our gradient. So we'll do define grad of x, and we're going to have it return jax.jacobian of our Rosenbrock function. And we have 3 variables with x in them, so we're going to use x all the way out to the third. And we're going to do plus x3 multiplied by jax.jacobian of our constraint function as well. And again, we're going out to the third x value, indexing out to the third x. Next thing we're going to want to do here is we're going to do a JAX just-in-time compilation. So the way we do that is we do at jax.jit. And what this allows us to do is basically it really speeds up the process of our iterations along with basically all the calculations going on behind the scenes. And then the next thing we're going to want to do here is we're going to define EQS of x. And what we're going to do here is we're going to concatenate using JAX. So return jnp.concatenate. And what that means is we're basically going to put 2 things together, and we're going to combine 2 things and string them together. We are going to concatenate our gradient. So we're going to do grad of x. And then we're also going to do the constraints of x. So we're going to do jnp dot at least 1d of constraints of x. And now we have compiled those 2 things together. And we've also got it JAX JITted. And again, JIT stands for just-in-time compilation. And that's really going to help us speed up the calculation process. The last thing we need to do here is provide some initial guess values of x naught, and then run our program and see what our minimization is. So let's do x naught is equal to jnp.array of, we're going to give it 4 values because we have up to an index of 4. So let's do 0.1, 0.1, let's do 10, and let's do 1. And notice here I'm using all floating points because when we're doing calculations within JAX with these gradients, we need to have floating points. And then from here, let's do x, comma f, so our x values and our our function value is equal to Broyden of EQS, and then our x values, which is x naught. And lastly, let's print x, and let's also print Rosen of x all the way up to our third values. So let's run this program. And hopefully with our Jack's JIT, it speeds up a little bit. And as you can see, we get our answer to be 0.0725. Let's double check by adding max iterations. So remember earlier we have 100 max iterations to be set up normally. But let's change that to max iter equals 500. So we'll change our iteration to a higher number and see if we can get a better, more accurate answer. It's running its thing. Jack's JIT is doing its thing. Any minute now. If I had a faster computer, it would be better. But as you can see, our number got closer to a different value. So we got to 0.0856 as opposed to 0.07. So increasing our iterations got us closer to the true value. Alright, and that concludes our video for using the Broyden's method along with the Sherman-Morrison formula and slack variables and the Lagrange multipliers to minimize the Rosenbrock function subject to constraints. I hope you guys learned a lot and had fun coding and learning about this method. I know I had a lot of fun with this, and it's super useful when we're talking about nonlinear equations that we need to minimize. So make sure you guys like, comment, and subscribe, and I will catch you guys in the next one.